Hi, I'm Doyle Bishop of Tulsa Heaters Midstream, otherwise known as THM. And today I want to talk to you about a component on a heater. Obviously one of our heaters or also other people's heaters. And it's what we call a fin. What is a fin? Why do we need fins? Where are fins? How are they made? What are they made of? And so on. So let's talk about that. So this is one of our heaters configured like we would configure it. It has a radiant box. The radiant box is where the flame is, and it's where the helical coil is, and it's where radiation heat transfer takes place. This is the hottest part of the box. This is the hottest flue gas. Obviously the flame is here. And fired heaters are almost always counterflow. You have the coldest process coming in, and it sees the coldest flue gas going out. So it's counterflow. And also on the hot end, the process fluid comes out. So we got the radiant box with a helical coil, and this is a bare coil, meaning it's just bent pipe with nothing attached to it. Then you get to the convection box, and as the name implies, you have convection heat transfer. And that's where you have the fin. Fins are actually located on the outside of the coil in this convection box pipe. So this real thick part is the wall of the pipe. And then this part in here, this is the base of the fin. And then this segmented part is still part of the fin, but it sticks above the pipe. This one looks to be about like a 1-inch fin, which is pretty typical for a maximum height of a fin. And if you look close, you can see that it's actually welded onto the pipe. It's a special machine that will weld that finning on there. So one of the questions you might have is, why use a fin? Why not just use pipe? Well, heat transfer is really about surface area. I want to create surface area for the heat to go into, whether it's radiation, actually you need it for radiation, but in a convection box, you need surface area for the convection heat transfer to go into. I could do that with just pipes. I could make this convection box just bare pipes with no fins. Look at this specimen here. Look how thick the pipe is. Well, this surface area is probably, I'm going to guess, probably about 5% of the surface area contributed by the fins. So in the same length of pipe, I can have 95% more surface area. And look at the thickness of the fin. So from a weight standpoint, if I were to do all of this with just bare pipe, I would probably have 10 times the weight of steel in a heater than I would with just a thin fin that's picking up heat. The fin doesn't contain the pressure, so you don't need a thick piece of metal like you do with the pipe, because the pipe is doing the pressure containing. The fin is only transferring heat. So it's a way to get more surface area for a lower cost, lower weight. The other thing that would happen if I did it all with bare pipe, then I would have much higher pressure drop, because this coil would have to be a whole lot longer, and I would have more pressure drop, so more pump horsepower, compressor horsepower, depending on what you're pushing through that heater. So the construction, I mentioned it earlier. I'm just going to draw it here. Let me just draw it like this. Here's a section of pipe. And this is the wall of the pipe. This is the center line of the pipe. And I'm gonna enlarge it here. This fin is like a donut around this pipe. My goal here is to pick up heat from the hot gases. These gases travel through this convection box. So they have rows of tubes with fins. It travels through really fast, and it's picking up heat from that hot gases that's coming by. And I want to get that heat to travel down this fin into the wall of the pipe, and then ultimately heat up this fluid inside the pipe that's rushing along the pipe. So this connection here is important. In some industries, like air coolers, they would take a fin and they press it on here. They just press aluminum fin and they press it onto the pipe. you want to make really good contact. And that works for an air cooler because it's low temperature air. It's not subjected to high temperature flue gas. Well, with high temperature flue gas, you can't press it. You've got to weld it off. Here you can see how it is. You can't really tell the difference between where the fin stops and the pipe starts. It's really good contact, which allows for this heat to flow from the fin into the pipe wall, into the fluid, which is what we want. So one of the questions might be is, this fin was only 1 inch tall, right? Why don't we make it 8 inches? Think about that. If I got a pipe here, I'm gonna really exaggerate it. Let's say that I had a fin that was this tall. I kind of think of it like a frying pan. If I have a really long handle on the frying pan and I grab it out on the end, I can't even tell that the frying pan's even frying because it's so far out. That heat doesn't want to travel 6 inches and ultimately get to the pipe. So you have kind of a limit there of, hey, am I effectively getting the heat from the fin into the pipe? So I can make it too long. So typically a maximum dimension from the surface of the pipe to the edge of the fin is about 1 inch. That's it. So look at this diagram here, this drawing. This is a cross section. This would be if I took a cross section here and looked at it. I'm going to see all these pipes. So this is fin. You can see the diameter of these. These are fin. And if remember, it's counterflow, meaning that maybe I have 1500 degree gases here. This is flue gas that I'm using to heat the process fluid. But on the back side here, maybe I'm 500 degrees. So question would be, and if you were sitting here, I'd wait for you to answer it, but I'm going to answer it since you're not sitting here. Question would be, would I put more finning here or more finning here? Well, the answer is think about that. I have really hot gases here. I don't need the same amount of finning here because it's so hot as I do up here. As I get colder and colder, I need more and more fins. So the fin density gets really high or higher as you go up into the convection box. You might say, well, we want to be really efficient. Let's put really big, high amount of finning in the lower section of this convection box. Well, if you do that, you can overheat the fin. I can be 1500 degrees here on a fin. Let's say if the fin's carbon steel, that's too hot. It's going to be too hot. In fact, what we'll do on all of our heaters is we'll have some bare rows. We'll have rows that take some of the heat out without finning. And most of the time, there's actually 2 bare rows. So we'll have a couple of bare rows. That way, when this gas hits this fin, it's not too high for carbon steel material. The last thing that you need to think about and consider is sometimes certain processes, this inlet temperature might be 80 degrees. This is the process inlet coming in. Believe it or not, at 80 degrees, I have to be real careful so I don't condense water on this pipe and on the fin. So I have to be cognizant of how I do my finning to make sure that I don't form droplets of water, which can contain carbonic acid, and then I've got a corrosion problem on the fin. So I need to look at that, evaluate that fin temperature, or actually the tube metal temperature, to make sure that I don't get acid corrosion as a result of just being too efficient with my finning. So in summary, fins are your friend. They make your heater efficient and they keep the cost down. Hey, thanks for joining. If you enjoyed this episode, hit like or subscribe to get more information about process heating and Tulsa Heaters Midstream.